Okay, the recording started now. All right. Yes. Good evening again, those people who have joined now. So, as always, this will be a formality always. I will be introducing myself in all the sessions, and also I will be introducing the course also. So, anyway, the course name is Analog IC Design, right? And it's an NPTEL MOOC course or Massive Open Online course. The instructor for this course, there are two instructors for this course. They are Dr. Sankaran Aniruddhan and he's a professor in electrical engineering at IIT Madras. The other professor is Dr. Nagendra Krishnapura. He is also a professor in electrical engineering at IIT Madras. Right. Myself, my name is Mayank Anupam. I am a tutor for this course. By tutor, I mean we conduct these discussion sessions, right? So these are called tutorials. So I am a PhD student in the Department of Electrical Engineering at IIT Kanpur. So I introduced myself last time also. Anyway, so again, I see some people have some doubts regarding recorded problem solving sessions. So yeah, again, as I told last time, these sessions that I'm conducting today, and all the sessions that will be conducted in the future, the weekly sessions, everything will be recorded and they will be posted on on my YouTube channel. Okay, the link for the lectures, for the recorded sessions, they are all I think shared with you. You can access them on the website, on the NPTEL website or SWAM website, whatever you are using. You can access it from there. So do you guys I mean, were you guys able to access the recordings? Can someone please confirm? Anyone? Was the link accessible to you?
Yes.
Yes, thank you very much. So those who have not been able to access it, let me just quickly tell you how you can access it. So this is the website, okay? I am using Swayam website here. So from here, you just need to go to what? These are the problem solving session, right? So at this point, you have to go, and then here you have to click, and this will take you to a different page, and here you click on the link. All right. So here you can see these are the so only week one was conducted last week. So there you have the YouTube link here, and then you also have the presentation folder link. So whatever notes I am preparing, they are also posted in this particular folder. All right. So I hope you are able to access it now. Anyway, so we were at so before starting with week two, let me just ask you, were you guys able to solve week one assignment? Any
I
doubts there?
I have I have a doubt in
All right,
figure
go ahead.
two actually.
Week one, right?
Yes, week one.
Okay. So what is the doubt?
It's like the doubt is the actually it is an ideal op amp, right?
Yes, it is an ideal op amp.
How I am approaching is the 100 micro amp is also flowing in this 40K and 60K also.
Where is that question? Okay, second question. Okay, all right. Yeah.
Yeah, yeah,
Okay.
figure two.
Yeah.
here.
Huh?
Through the ground, the current will be zero. So the same 100 micro will flow through 40 kilo ohm.
No, no, come again. Why is the current zero through the ground? Why do you say that?
Yeah, normally in through ground, the current will be zero, right? Can I go
No,
this approach like 100 micro will flow through the 40 kilo ohm?
no, it will not flow through 40 kilo ohms. No, that is not right. You see, the way it is drawn here, it is actually not correct. You have to assume that there is a voltage source somewhere. Okay, there is a source somewhere. See, there cannot be just one ground, isn't it? There has to
Okay.
be a voltage source somewhere, right? There has to be
Uh,
a supply somewhere, isn't it?
yes, yes.
I mean, that's why it's like this actually. I'll tell you. Mm, I'll just take week 1, 9. Yeah, similarly, right? It was a similar question to this, isn't it? Let me just
Yes, yes.
copy and paste it. Oh, 1 second. Just use this figure. Okay. So you have to. This is the situation, right? In which you have instead of this voltage source, you have a resistor, right?
Yes, yes.
So what is the resistor? There is a resistor placed here, I hope, right? And then
Yes.
there is a current source here in this direction,
Uh,
let's say. So it is, let's say, 40 milliampere or 40 micro. What was it?
100 microamp.
Oh, 100 microamps. And what was this resistor here?
20 kilo ohm.
20 kilo ohms. And then you have this is 40 and 60, right?
40, 60. Yes.
Correct. This is the
Yes,
situation.
correct.
Yeah.
Correct.
So I understand your confusion. You are asking that the net current through this point should be zero because there is no other place, right, for the current to go. That's what your question is,
Yes.
right?
Yes, sir.
Yeah, but that is not
Yes.
going to happen. See, because the current that is coming here, the current that is going to come here, this 100 micro is
Mm.
going to take this path and it's going to disappear inside this op amp. Okay.
Oh,
This op amp, it's an
okay.
ideal op amp, so it can take in as much amount of current as possible. It can take any amount of current. I mean, so that kind of an assumption is not true, whatever you are saying. All right. The path that this current
Okay.
will take is in this manner. So once it takes this place, once it comes here, after this,
Mm.
no one knows what is going to happen. Right,
Okay.
op amp will do its own business, it will do its own magic and make sure that the voltage relationship is satisfied because the op amp has to maintain a certain voltage outside, right?
Yes, yes. Okay.
Yes, so that will be maintained. For that, how much amount of current it has to consume, it has to take some current, right? It will take some current, it will maybe push some current out. Doesn't I don't We cannot say what it will do. The only thing that
Mm.
we can guarantee is the voltage relationship will be maintained. And with that voltage relationship, once you know what is the voltage, you can then find out how much current it is actually taking or pushing out. All right.
Okay.
Yeah, fine. Any other doubt in week 1 assignment?
Yeah. This is my doubt only. Thank you.
Okay, welcome. So other people, were you able to solve it? I mean, I covered the most tricky part in this, which was to find out whether the loop is in negative feedback or positive feedback. So after that, were you able to solve this question? These two questions. So if there is no response, that means all right. Okay, fine. Very happy to know that you were able to solve it. Anyway, so I hope that the idea of negative feedback is clear to you now. Is that clear now? The idea of negative feedback? What is it? How and how it is working? Negative feedback, because now week 2 assignment also you might have done, and also week 3 lectures are also uploaded, right? So you must have a good enough idea what negative feedback is, right? And how it works actually. So today, actually, today we are going to look at a very common problem associated with negative feedback, which is of delay. Okay, and what happens when you have delay in a negative feedback, right? So while going through the lectures, did you guys have any issues following the or understanding the problem of negative feedback or uh, problem associated with delays in negative feedback? Were you guys able to understand this? You see, because today on whatever was taught in week two, I will not be able to form a lot of questions on that. It's just for understanding. The things that were covered in week two are more for your understanding and less for problem solving. All right. So that is why you have to. So this session today will mostly be for discussion and not for problem solving, because there is not much problems to. I mean, one can go ahead and make really complicated uh, problems, but that is of not a lot of use. Okay, well, ultimately, when you will be doing this, it will not be you will not be using pen and paper. These analysis will mostly be done by your simulator, but you have to understand it. So the understanding part is very important. So that is why I am asking you all. So were you able to grasp the core idea? So maybe you can tell me how what you understood, what happens with delay. Maybe you can help me out. Someone, please. See, if you do not say anything,
We
yeah, Ravi, go ahead.
we we with the delay introduced, we have this oscillatory behavior coming into picture. And like instead of attaining the steady state
Uh-huh.
in one go, I mean there are oscillations which can die down, but that depends on the amount of delay
Mm-hmm.
and also on the amount of acceleration. I mean the way we are starting, so it can get
Correct.
worse. But there will always be the oscillations present due to delay, and we need to minimize them in order to have a robust system.
All right. So I understand. So you are basically going with the analogy of bike, right? Bike driving, bike riding, right?
Yes, yes.
Yes. So correct. So that is the one of the greatest analogy, right? So you that's actually how negative feedback actually works. So for negative feedback to work, what is the basic idea? We know that. So let's put a heading here. Okay. So for negative feedback to work, we know that there is certain input, right? There is certain input which is, let's say, vref, or whatever you want to. Let's say let's not call it vref. Let's call it some reference. Okay. We'll make it a general kind of negative feedback system. General negative feedback system. Okay. So there is a reference here. All right. And then you have your output here. Okay. You have some output. All right. Now, how negative feedback works? You make sure that a part of the output is is sensed by the equipment or machine, whatever you have. It is sensed by the equipment with some gain factor k, and then it actually is fed back to the input. Right? It is again fed back to the input. That's how and the name negative feedback comes because there is a negative sign associated with it, right? And then basically the error is then processed. There is then processed, and after processing, this controller here, it sends an output, right? That's how the negative feedback works, isn't it? Isn't it?
Yes.
Yes. So instead of putting a negative sign here, let me just put this gain k as minus k, right? So that's the same thing. Okay. So this is how negative feedback actually works. Now, for the negative feedback to work, we know that again, if we take the example of bike riding, as our friend also suggested, what happens is we start our bike. Let's say our aim is to achieve 60 km per hour. That speed we cannot exceed that speed, but we are in a hurry to go somewhere, so we cannot also go below that speed, right? So we want to maintain a constant speed of 60 km per hour. So that speed, if we want to maintain, what are we going to do? We are going. Our only friend is going to be speedometer, right? We cannot rely on anything else. Our speedometer is only our only friend, right? Only that is the correct measure of what is our speed at the moment, right? So we are only going to rely on speedometer. Now, how is the negative feedback working here? Again, Ravi, since you were the guy who made me understand, so who spoke, so I will ask you again. How is the negative feedback working in this particular scenario in the bike riding example?
When we see, it depends on the output and the input. So on the
Okay,
speedometer, when we see the speed is less than what we want, let's say
okay,
we want 60, the desired is 60. But if
okay,
it is less than that, then we'll accelerate and try to speed up the system, the bike.
yeah,
Uh, and I mean, in ideal case, if there is no delay, so in that case, when we are getting on the speedometer, whatever value we are looking, that is
uh-huh,
the input, that is the feedback to us,
uh,
and based
okay,
on that feedback, we'll either speed up the bike or lower down the speed.
correct,
So if it is more than 60, we'll lower down it, and if it is less than 60, we'll speed it up because that's
right?
that's what we desire.
Correct. Exactly. Right. So, but what happens? That's how negative feedback works, right? So, the negative feedback is actually what is the negative feedback here? It's you. How is the negative feedback system here? What is the if someone asks you, tell me what is the overall control system here? Tell me which entity are acting as what. So, what will you say? So, your speedometer is what? Speedometer is a
That's a
sensor.
sensing element,
Correct. That's a
sensing.
sensing element. And then with that speedometer, once that senses, which is the part that actually takes the control, which actually makes the decision, which actually
Um,
does this job of negative subtraction, one which does this
uh,
subtraction thing.
that's our brain, we
Correct.
ourselves. I mean,
Exactly. So that is the brain. Brain actually does this. Brain actually knows which direction we have to go, and then what is actually it where is it is the actual speed. What is the actual speed? So based on that, brain is doing a calculation inside, right? It is saying, okay, I am closer, so I maybe want to increase the speed only a little. I do not want to accelerate it very fast if I am very close, right? If I am very far away, let's say my target speed is 60 km per hour, but let's say I'm 40 km, I'm actually going at 40. So brain knows that okay, I'm very far behind right now. So maybe I need to accelerate very fast, right? Brain knows that. So it will what will it say? It will give a direction to our hands, right? Hands and our legs and our feet, right? So accordingly, our hands and our feet will behave, and then they will pass on that control information to the bike, right? And then the bike will act accordingly. So that's how negative feedback works. Now, what happens if there is a delay in the system? Once there is a
um,
delay, yes, Ravi.
yes, I mean, if there is a delay, then whatever the speedometer will show, that will be the past value. I mean, of the output. The actual speed won't be that. It
Yes,
will be like the delayed version of that speed.
yes,
So based on that, when we are processing, it's not the correct information actually. So our acceleration or deceleration might also be delayed as per
yes,
that. I mean,
exactly. And that can lead to a lot of issues, right? Isn't it?
yes,
Now, I think you were the only one, right, who asked me last time what happens if there is a delay in the system and because I said that loop gain has to be very high, right? Loop gain has to be very high
uh,
for the loop to work, for the negative feedback loop to work accurately, right? That's what I said last time.
yes,
And I think
yes.
you asked me this question that what happens if there is a delay in the system? Where,
I actually asked what happens like if we have this closed loop gain very high. So will it oscillate? That's what I.
oh, you asked, okay, I thought you asked a different thing. So okay,
Yeah,
anyway,
then
so
you told me that it might be delayed.
yeah, correct. So they actually the delay is the one that causes a lot of problems. So see, if there is a lot of delay, right? If there is a lot of delay in the system and your loop gain is very high, which means that uh, if you want to draw an analogy here, loop gain being very high, how can you draw it in the bike driving example? Can you think of it? Can someone think of a perfect analogy of high loop gain in the bike riding example? Okay, let me help you. So, by high loop gain, what do we understand? The loop works the loop is very powerful. The negative feedback is very powerful in trying to negate, in trying to bring back the system to its original state, right? That's what high loop gain means, right? The loop is working very powerfully. Which means that if you try to draw an analogy in the bike riding example, it means that let's say you wanted to achieve a speed of 60 kmph, but your actual speed is 40 kmph. Okay, then what will happen is high loop gain means you are very aggressive. Okay, you will instantaneously accelerate to a you will accelerate at maximum possible uh, acceleration that the bike can support. That's what high loop gain means. Understand? So there are two types of guys, right? If you want to go from 40 to 60 kmph, you can also accelerate slowly, right? But there is another type of guy who will accelerate very fast, isn't it? Aggressive drivers, aggressive riders. So high loop gain, you can understand it's an you can draw an analogy in that sense. High loop gain means a very aggressive loop which will work very powerful, which is very powerful in processing the output again and sending it back to the input, something like that. It's a very aggressive kind of a loop structure where the loop will act very powerfully on whatever the output is fed back. Got it?
Yes.
Yes. So what is going to happen if you have a delay in that situation? Again, if the loop gain is very high, which means the loop is very powerful, and in that situation, let's say you have a delay in the system, what is going to happen?
So we might based on that we might get over the desired value or like below it quite fast and uh,
Right.
but
Exactly. So yeah. So again, let's say this was the 60 kmph speed desired, right? But let's say you are here, somewhere here, not 60 but 57. Okay. Let's say you are somewhere here. What is going to happen in situation where there was no delay? Your loop is very powerful. So what will it do? It will it is very fast. So that is why it will come here and it will settle here very soon, right? It will settle very soon, correct? But in
yes.
the event that there is a delay in the system, the same kind of a thing, same kind of a loop, if there is a delay, what will it happen? What will happen? What will it do? Once when it is 57 kilometer per hour, the speedometer is stuck somewhere, right? It is sorry, not stuck, but there is a delay in the speedometer. So maybe it might speedometer might be showing a reading of 50 kmph. Okay, so the loop is very powerful, mind it. Okay, so what will it do? It will make it suddenly it will accelerate it in such a manner that it may go out above 60 kmph, right?
Yes.
It will go above 60 kmph. Now, once it goes very high, because the loop is very powerful, right? So maybe it might have gone to 100 kmph. Okay, once it went to 100 kmph, only then the speedometer say that okay, it has actually gone above 60 kmph, and then it will start reducing it, isn't it? But mind it again that the loop is very powerful. So what will it do? It will immediately very powerfully reduce it to a very low value, isn't it?
Yes.
Yes, and let's say now it has went down to like 30 kmph. So you understand the problem now, right? You understand the problem now, right? That it might do this kind of behavior. It may never stop. It may go. It may keep oscillating. It will never stop, isn't it? And this happened because of two issues. There are two things which are making the situation very bad. First, there is a delay, right? So delay is something which you can never get away with. Okay, if this is a real system, there will always be a delay, right? Because you cannot because any physical system cannot um has to obey causality, right? You have heard about causality principle. Causality. Have you heard about causality principle? So causality. One second. Have you guys heard of this term, causality? So causality simply means that uh, basically it means that the cause cannot sorry the effect of something cannot precede the cause, which means that without doing something you cannot expect a result. The result cannot come before you do that thing. You understand? It makes sense, right? In the real
Yes.
world it makes very sense, it makes a lot of sense, but that anything for anything to happen, something has to uh, happen first, right? Only then the result will come, otherwise it cannot come before the you cannot expect a result before the deed, right? So once the deed is done, only then can you expect a result. So that is what is causality, right? So so because of that only, for any real physical system, you cannot expect a output before the input is applied, right? So delay cannot be less than zero. That is guaranteed, right? But it turns out that delay also cannot be zero. If there is a system, it will take some time to process something, right? If you want to take the worst or the extreme case of it, you know that nothing is faster than the speed of light, right? So for any information to be processed, it cannot happen before the time it takes for the light to pass through that system, right? It cannot happen before that. So that is the extreme case, but it turns out that the real system has have a lot of delay. So the thing is that so you cannot get away with delay. You cannot get away without delay in the system. So delay is something which is going to be there in any in any physically realizable system. So, but what is the another issue in this? There is delay in this system, but there is also another issue. What is that? With the delay, the system was very powerful. The feedback was very powerful. It was very fast. The feedback was extremely fast. Mind it. I'm saying that it is extremely fast. The feedback is extremely fast and it has a lot of gain. Okay, it is very powerful and it is very fast. So please mind these two words. Feedback is very powerful and it is very fast. So I will just write it anyway. Mm, So at present, I have only written very, right? So this is qualitative. So what is very high? When so this term very powerful, very fast. These are all comparative, right? At some in some cases this may be very fast. In some cases this may be not so fast. So what is it that decides this relationship? When is the speed very fast? When is the feedback very powerful? For this particular delay, the loop is very fast, right? It turns out for this particular delay, that the delay that is there in the system, the loop is very powerful and is very fast, and that is why before the loop could really understand what is happening, what is actually happening, the system has already taken the action, right? So you understand what I'm trying to motivate here. I'm trying to motivate here is that uh, when there is a delay in the system, it becomes mandatory that at certain point your loop has to become slow. I mean, uh, so let me rephrase. So when your loop is actually when your loop has a delay in the system, when your loop has a delay in the system, what happens is you have to make sure that the loop becomes slower. If your loop is very fast, What happens? What will happen? The same situation that you have seen here. Are you guys able to understand that? I mean, does it make sense? Yes, Ravi.
So essentially, what you meant was, I mean, it's always with respect to delay, we have to see how fast the loop can get or how
Yes,
slow it can get, right?
yes, exactly, exactly. That is the
Okay,
point that I
so
was trying to make through. Yes,
thank you.
yes, and that is why uh, in any system, if there is no delay, if let's say you found out, you analyzed an you analyzed a closed loop system, you find out how it will behave and everything. But let's say once the delay is increased, you have to make sure that the loop is slowed down slightly. If the loop is very fast, still very fast, as in the case of without any delay, the loop will start to, the loop can go very close to instability. Okay, it can become, it can go very close to instability. It can become unstable also. Okay, so it all depends upon how much delay you have, and with respect to that only you will decide how much, what is the speed that you can target for this particular loop, isn't it? So this is the whole idea behind. I mean, if you understand this thing, I am sure you will be able to, you will be able to follow the next week lecture, which is week 3, very easily, because this is the core principle behind Nyquist criterion for checking stability and everything. So this is the core this thing theory behind that. So this is the intuitive understanding of what happens when you have a delay, in the system. All right. Okay. So now that is done. By the way, any doubt? So there was a lot of mathematical calculation done in that particular in this particular week. I would encourage you all to try this out on MATLAB. The equations that the instructor showed, and the plots that he made, that he showed. You can also try to recreate them on your own in MATLAB. If you do not have MATLAB, you can also use Octave. So that is a free thing. That is a open source software, Octave, and maybe write it. So GNU Octave.
So I have one doubt.
Yeah, go ahead.
So previously, basically, you are saying if the difference between reference and the feedback is more, the loop should react fast, and if the difference is less, the loop should react slow. That's what you are trying to say, right?
No, I'm not trying to say that. See, what you are saying is if the difference is, so that is the uh, working of any loop. Any negative feedback loop will actually see the difference, and based on the difference, it will send a signal, right? If the difference is very large, it will send a large amount of signal. It will send a large amount of this thing. It will say that, okay, there is a lot of difference. You need to do something. Uh, Whatever you are doing, you need to do it more of that, right? If the difference is smaller, so what will the loop say? Okay, you are getting closer now. Maybe you can reduce what you are doing so that you can achieve the steady state. Are you getting my point? But
Yes, sir. Yes, sir. Got
but
it.
yeah, so now what I was trying to say is, if there is a delay in the system, okay, if there is a delay in the system like this, if there is a delay in the system like this, then you have an issue, right? If there is a delay in the system, what will happen? um, let's say you were already very close to 50 this target speed 60 kmph. You were, let's say, at 57 kmph at that time. Okay, so what should the loop have done? Loop should have said that, okay, you are very close, maybe you have to accelerate, but not do not accelerate in that at that speed. Do not accelerate it, do not go very do not accelerate at very high this thing speed, if you understand, right? If you understand what I mean. So do not
Yes.
increase the acceleration a lot, because now you are very close to that target speed. However, if the loop has a delay in the system, the what will happen? When even when you were closer to 57, the speedometer was showing a reading which was 50 kmph, right? So what will the loop say? The loop will say,
Right.
okay, you are actually far behind 60 kmph, 50 kmph, right? So you are far behind, you have to increase the acceleration, right? That's what the loop will say. However, you were very close, mind it, you were very close actually, but the loop was saying that you are not that close. Speedometer is saying that. So there is a delay, right? The speedometer is delayed here. So what
Yes,
will
sir.
happen? Your speedometer, sorry, you will increase the acceleration very strongly, right? You will increase the acceleration very strongly. When you do that, you actually will overshoot, isn't it?
Yes, sir.
Yes. And let's say you are a very aggressive driver. Let's say you are a very aggressive rider, which means that once you will actually increase the acceleration increase the acceleration a lot, right? Because aggressive drivers, what they do, they will, if they want to achieve a certain speed, they will simply turn the accelerator to the maximum limit, isn't it? And once they hit that point, then they will suddenly decelerate. That's what your aggressive riders do, right? So let's take those aggressive riders only in this particular example, that the rider is very aggressive and there is a delay in the system. What will happen then next? Once it reaches, only when it reaches this 100 kmph, the speedometer starts showing that okay, you have actually exceeded 60 kmph. So it is again delayed. Speedometer is delayed. So let's say once it reaches 100 kmph, the speedometer shows a reading of 61 kmph. Okay.
Yes, sir.
Once it reaches 100, the speedometer shows a speed of 61 kmph. So what will it do then? You are again a very aggressive rider again, mind it. So what will you do? You will again reduce the acceleration to the minimum, isn't it?
Yes, sir. Basically ringing at
Yes,
the output.
exactly. And what can happen in this particular example is that this ringing will never stop. In fact, this will keep on increasing. You understand the behavior because you are a very aggressive rider. You take a decision in extreme decisions, isn't it?
Yes,
Which,
sir.
if you translate it in the in a controller example, we say that the loop is very strong and it is very fast. Okay, that's what it means. That's what we mean to say when we say that the rider is very aggressive. The rider is a very aggressive, which means that that particular system has a feedback loop which has a very high loop gain, and it is very fast. That's what it means. Got it?
Oh, okay, yeah, but I thought like you wrote there, right? Feedback is very powerful. I thought like feedback powerful means high loop gain. So
Yes, it is
that we can,
actually, that means that only. This
yeah,
feedback
that I
means,
can understand that there is less error between the reference and the feedback signal. But fast, I thought it will be very fast reacting. Then we shouldn't be having ringing, right? That's why I got this out.
oh, acha, understood. What is the, okay. So, okay, I actually made a mistake here. Yeah, you are actually right. So, when I say feedback is very fast, which means that it is not feedback that is fast. It is this part which is very fast. Okay. For once the error comes here, the controller will also take some time, right, to process that.
Yes,
Right? So that is very fast. If that is very fast, this will actually, this situation can occur. So that's what I am saying. If the if there is a delay in the system, if there is a delay in the uh, system somewhere, you'll have to make sure that it is again slowed down. I mean, this might actually sound very counterintuitive in that sense, but if you take the understanding here, you will be able to understand it. If you take the example here, you will be able to understand that if there is a delay here, to make sure that the loop actually works properly, you will have to introduce a delay here also, right? You understand?
yeah,
Are you
got
able
it,
to
got
follow
it.
it? I mean, this actually might sound very counterintuitive, but that's how it is. In the if you when you go further, you will see that when there is a delay in the system, you will have to reduce the unity gain bandwidth of the loop. So that will come later. Unity gain bandwidth actually translates to what is the speed of the loop. Okay, that's the meaning of unity gain bandwidth in a loop. So when there is a delay in the system, you have to make sure that the unity gain bandwidth of the system actually reduces, which means that it will be slowed down slightly. Because it is slowed down, it will be able to then it will be able to work properly, isn't it?
Got it, got it.
Got it? Yeah. Thank you. So Ravi, you have a question. You have raised your hand.
Yes, so I mean the case when we say about very high loop gain when we started with all this,
Haha.
that is just the ideal case, right? But in practical system, it's not never gonna happen.
Then it
So
there is always a limit, okay? High and low is always comparative. There's in some situation, okay, so let's take an example. Thousand, let's say thousand. So if I simply say thousand is high, you cannot say whether it is correct or not. But thousand is high compared to one. That is correct, right? Thousand is high compared to
uh,
10,000. That is wrong. So there will
mm,
come a situation when a certain loop gain value will actually be very high for a particular because the delay in the system is very high. Got it?
yes, so I meant like in ideal cases, we won't have any limit for the feedback loop, right? The strength of the feedback loop. But in
Yes,
I mean the practical cases, we will have that. That's
that
what
is
I'm.
true, and that is
That's
why.
okay.
Okay, so uh, in practical situation, yes, you have a you have a limit to what is the value of this thing that you can get. Okay, and that is but it turns out that even that may be very high sometime. Okay, and you may have to reduce even that.
Okay. And like you said, the unity gain frequency. So that
Uh-huh.
means that I mean we'll have to reduce it means we will have to compulsorily reduce the bandwidth of the system
Yes,
in
yes,
order to make it stable,
yes.
right?
That will come later,
Okay.
but this is the
Okay.
intuitive understanding of that. If there is a delay in the system, you have to make sure that the loop actually doesn't work at very high frequencies. Okay, it is not able to process very high frequency signals. It actually has to slow down. If there is a delay in the system, the loop has to slow down further to respect that delay.
Right.
Got it?
Got it. Yeah.
So
Okay.
that is very easily understandable if you look at this example. If there is a delay in the sensor part of the loop, that is in the feedback part of the loop, then you have to delay this part also. Only then will the loop work. Okay. So you again have a doubt, Ravi. You have again raised your hand.
No, no, sorry, that was previous answer.
Okay, fine. So I hope this is clear. This is clear, right? I hope this is clear,
Yes.
right? All right. So if this is clear, I don't think I have anything else to discuss today because, yeah, I wanted to ask you, there was a lot of maths. Okay, so yeah, I was saying this. You please try to recreate the plots on this particular software. If you have MATLAB, it is very good. Use MATLAB. If you do not have the licenses to MATLAB, use this particular software, GNU Octave. It is actually very similar to MATLAB, and for all the things that you will need, Octave should be enough. Also, it is also very good exercise for you to learn how to use Octave because this is a software which actually handles a lot of because you will build a lot of understanding if you keep um, plotting things. Okay, because pictures are worth 1,000 words, right? You have heard this saying a lot of times. You will keep hearing this. So it is always good to visualize to understand by seeing the plots because then you will be able to visualize it properly because you will see the picture of what is happening, right? Even in the case in this particular lecture series, this particular week's lecture, I am sure you might not have been able to understand if Professor Nagendra didn't show you the plots. Would you have been able to understand without seeing the plots what is actually happening?
Uh, yes, I mean visualizing them was more
Yes. So exactly.
intuitive.
So simply solving equations will not give a lot of intuitions. It is only when you start seeing actually what is happening, then you will understand what is actually going on. Okay, so for that only I'm advising you strongly use Octave to plot. In fact, all the equations that were covered in this particular week, sorry, yeah, in week 2, please try to go back and use plot them all on Octave, and you should get a same kind of a plot that Professor Nagendra was showing in his lecture. All right. Okay, so now I think that is done. I'll simply just ask you, simply just for completeness, for sake of completeness, just go through the assignment that was shown in this week. I'll just ask you, So do you guys have any doubt in the assignment 2? I mean, understanding wise? I don't think so. You should be able to solve it.
So I have a doubt regarding this unity gain question. In question number 6, I guess there was a question regarding unity gain.
Where is that? This question number 5, right? Determine frequency at which gain
Yeah,
drops
fine.
to 0 dB in kilohertz.
So there are actually two ways, right? I can use the gain bandwidth product, or I can equate the transfer function to one.
No, no. What is gain bandwidth product? What are you saying? The op amp is ideal. There is no negative feedback. The question of negative feedback is not there. You see, what you are talking about is, I think, loop gain being equal to this thing, 0 or whatever. Here, the loop gain bandwidth is infinite, isn't it? Is it infinite
Oh,
or not? Okay, tell me whether it is infinite or not in this particular case, the loop gain.
No, sir, it's not. It is not infinite.
no, it is. There is a DC gain.
Loop gain is, there is a TC gain in the loop. Loop gain, I'm asking about loop gain, not the closed loop gain. I'm asking about negative feedback loop gain, the loop gain that you have heard. Okay, let me just talk about it. It's good.
That is infinite if we consider op amp gain.
Yes, exactly. So, uh, let's just talk about it a little bit. So, this is the question, right? You have this, sorry, pardon my drawing, not a very good thing. I do not draw very well. By the way, why am I doing this particular thing? I'm drawing this dots here. Why am I doing that? Can anyone can anyone say what is the purpose of these dots?
Current division, uh,
These are junction
the
dots. Okay,
nodes.
these are okay. Yeah, you're
Yeah.
correct. So these are junction dots. Whenever you have more than two wires intersecting at a particular point, you have to give this junction dot. This is a convention schematic drawing. Whenever you draw a schematic, make sure that you follow this. Whenever there is a junction, and junction is a point where more than three or more wires intersect, you have to make sure that you put a junction dot here. Okay, follow this practice. This is a good practice. All right. So this is this thing, and then you have this resistor R1. This is R2. This is, and this is C, and this is A is equal to infinity, right? Because this is ideal case. And then you have this voltage source here, Vi. All right. So tell me, what is the loop gain here? How do you find loop gain? First of all, whether it is in negative feedback or not. Hmm? It is in negative feedback or not? Is it negative feedback or not?
It is
We do
negative.
have to test it.
Yeah, you have to actually test it. So that's what, whether it is negative feedback or not. Tell me,
It is in negative feedback.
it is a negative feedback, right? So how do you test whether it is a negative feedback or not? You do what? Tell me
We remove any sources first.
first. Okay, yeah, good, right. Sorry for that. Let's first remove the sources. So take copy and paste. I'm very sorry. I'm coughing a lot. Yeah. So you have to remove the sources first. What you have to do, instead of this voltage source, what should I do? What should I replace it with?
That would be a ground.
Yes. Yes, good. After that, what should I do?
Now we have to apply, so we have to break the loop
Yeah.
at like where where the summation was happening of the where we were getting the error basically or the
Yeah, so
difference.
see, okay, this is what I explained to you last time. In general, you do not need to break it at that particular point only. You can break the loop at any point. Got it? That's how the loop gain business works. You can break the loop at any
Okay.
point. It doesn't matter. The most then basically you have to ask the next question is okay. So where should I break it? There has to, I mean, if you can break at any point, there will be a point where it will be very comfortable for you, right? To do the analysis, isn't it?
Yes.
So that is the next question. So where do you think is most beneficial for it to break? I mean that such that it becomes very easy for us to analyze.
Input of
Probably
R.
where, yeah, the input of R and C,
Yes,
wherever
exactly.
that's
Good,
connected to.
good, good, good. So we will break it here, isn't it? We'll break it here, and then what will we do? We'll apply a test voltage, right?
Hmm.
Isn't it? We apply a test voltage here, and what we have to look for?
So at the same point at the return, what are
Yes.
we
So this
getting?
is the same point that is going to return, right? So this is the point which we have
Yes.
broken. Yes. So what should happen at this point? What should happen here?
So,
What are we looking for here, by the way?
um, so what is the voltage that we are getting? I mean, when we are applying V test, what is the voltage we are getting at that point?
Okay, so when we apply V test here, what is the voltage that we get here?
So that's so the output is gonna be minus infinity in this case.
Let's
We
say
don't.
minus A.
Oh,
Okay, we'll replace A with infinity
okay,
later. So it is minus A times
okay.
V test. Okay, all right.
Yes.
So what is the voltage that that we are going to get here?
Um, I mean, we'll do the division of this, so that would
Yes,
be some negative voltage, which will
yes. It will be some negative voltage,
minus.
right?
Yes.
So that's the telltale sign of negative feedback, isn't it? You applied some
Yes.
voltage, and in the return, you're seeing that that feedback is making sure that the that whatever is coming back is actually trying to suppress the initial excitation, right? So if it is V
Yes.
test is positive, which means that voltage is increasing here at this node, right? So what is
Uh,
coming back at this point? The return is actually making sure that the return is something which wants
negative,
to
so
reduce it, right?
and reduce this. Yes.
Yes. So
Yes.
this feedback is negative, confirmed. All right. So feedback is negative.
Yes.
Now tell me what is the loop gain? So I think
So
loop gain
that
is
would
covered
be
or not? Loop gain is covered or not?
uh,
Loop gain is covered.
yes.
Was it covered in the lecture till now? Loop gain? It is covered, right?
It's over it.
Anyway, so loop gain is basically you break the loop and you apply the test voltage V test and you see what is V return. Okay, and then you do this V return by V test. So that is loop gain. So tell me what is the loop gain here exactly? So because of
Uh,
applying of application of V test here, you get a minus A times V test at the output. And then again, what comes back as V return? What is V return?
A
we
times
return
that
to
R1 by R1 plus
Minus A
parallel
times V
combination.
test and then voltage division, right? So what is voltage division here? It will be uh,
R1 by
R1 divided by R1
R1
plus
plus R2 parallel 1 by SC.
R2 parallel 1 by. So what will that be? R2 into 1 over SC, right? Divided by R2 plus 1 over SC. So what will it be? What will it be? R1 plus, so it is R2 divided by 1 plus SCR2, right?
Yes.
And then this will be minus A times V test times R1 divided by this will be R1 plus SC R1 R2 plus R2, right? And at the top, all the denominator will go top here, CR2, right? So what will it give you? Minus A times R1 times 1 plus SCR2 times V test divided by this is R1, sorry, yeah, this is R1 plus R2 plus SCR1 R2, or if you take R1 plus R2 common here, it will become 1 plus, this is R1 plus R2, right? And this will go on top, R1 plus R2, right? So what is your loop gain? This is V return. So what is your L of S? V return by V test. What is that? Let's just
Minus
quickly
A
check.
R1.
Minus A
R1 upon R1 plus R2 into 1 plus SCR2
minus A
upon 1 plus.
times R1 divided by R1 plus R2 into 1 plus SC R2 divided by 1 plus SC R1 R2 divided by R1 plus R2, right? So tell me what do you see here? So what is the loop gain? Magnitude. So if A tends to infinity, what is going to happen to all the to everything? So if you ask about mod of loop gain, sorry, L of j omega magnitude. So what will happen to it if A tends to infinity? So let's,
For all frequency, it will be infinite.
so this will actually mean that this is also infinity, right?
Yes.
It will be infinity, isn't it? For all frequencies. So that is not a problem. So loop gain is actually infinity for all frequencies. Good. Now that we are clear on it, let's come back. So now tell me, the guy that was asking the question. So when the question is that determine the frequency. Oh, sorry. Yeah. So when the question is asked that determine the frequency at which gain drops to 0 dB in kilohertz, I'm talking about fifth question. Okay. Gain drops to 0 dB in kilohertz. So what is that? Which gain are they talking about? Which gain are they talking about here?
Closed loop.
Yes, exactly. So closed loop gain is is the one that they are talking about. So what do you think this system is actually? What is this system? What will V output with respect to V input? What will it behave like?
Integrator.
Yes, exactly. It is an integrator. Can you see the integrator action here? Let me just show you with this particular figure here. You see, we know that the loop gain is infinity, right? So this guy, this point here will also act like ground, zero, right? Voltage will be zero here, isn't it? Because these 2 points are shorted, right? I mean, not shorted, but virtually shorted. Correct? Correct? So this point here,
Yes.
it will be a virtual ground. So what will be the voltage here? It will be zero, isn't it? So what is the current that is going to flow? It is going to be Vi by R1, right? And this current is going through a parallel, is flowing through a parallel combination of R and C. So you know that if there is a current source like this and you have a parallel combination of R and C, what is going to happen? This is actually an integrator, right? The current is going to be integrated by this capacitor. So if this R was infinity, so you can see that this time it is actually very, there is no doubt here, right? The voltage at this point will be what? It's an integration of I times, so let's say it is I of t, so it is I of t dt by C, right? This is the voltage, isn't it?
Yes.
So even in the presence of this resistor here, there will be a DC term, there will be a gain term associated with I times R. There will be some DC term, and then there will be, I mean, it will behave uh, like a first order filter. Okay, it's an integrator only, but it will behave like a first order filter, something of this kind. Got it? So there will be a pole here.
Yes.
That pole will be equal to 1 over RC. So I hope you know all of this, all these things from your basic circuit analysis, right? Okay, good. So this is actually a very simple example. So this is an integrator, right? So for this particular integrator, the profile will be something of this kind. So they are asking what is the unity gain frequency, that is the point where this becomes equal to 0. Okay, this is what is being asked to you. By the way, this is very common. I mean, this is something which is used in actual designs also. People tend to use this particular integrator. Okay, using this integrator, people make you can make a lot of filter architectures. Okay, all right. Any other doubt in this particular question assignment?
Sir,
Huh?
sir, here correlated tolerances means the product of the tolerance. Sir.
No.
Okay.
You see, okay, this is something which is new. Okay, let me just talk about it a little bit. Let's say you have a resistor given. Okay, let's say it is 10 kilo ohms. When you buy it in the market, you will never get a resistor exactly 10 kilo ohms, isn't it? All
Yes,
right.
sir.
Let's
Yes.
say you have another resistor. You that is also supposed to be 10 kilo ohms, isn't it? So when you go to market and you ask for two resistors, you ask for two pieces, okay, and you want 10 kilo ohm resistance from there. So let's say they are both from the same company, okay. Even then, can you say that both the resistors will be of exactly same 10 kilo ohms? They will not be, right?
Yes, sir.
They will have some 10 kilo ohm plus minus, let's say something, right? 10 kilo ohm plus minus something, exactly, right? So let's say that something is let's say in this case 1 ohms. So with this 10 kilo ohm you have, or let's keep a 10% variation. So let's say 10 kilo ohm plus minus 1 kilo ohms, okay. So any company that sells a product, okay, sells a resistor like this, any circuit, any product, they will always say that this is the value, this is the typical value. Around this can be the variation, isn't it? So the typical value is 10 kilo ohms, but the variation can be anything between plus and minus 1, which means that the if you are buying this resistor, you can also get a resistor which is equal to 9 kilo ohms. You can also get a resistor which is 9.9 kilo ohms. You can get a resistor which is 10.1 kilo ohms. You can also get a resistor which is 11 kilo ohms. Got it? So all these are possible because they have said that this is the tolerance. Got it?
Yes, sir.
So this is the tolerance. Now, now when you say that, when you want to use these two resistors, when you want to use these two resistors in this particular filter, what is going to happen? you will see that somewhere in this analysis, you'll find out that the filter bandwidth. What is the filter bandwidth in this case? It will be what will be filter bandwidth in this case? Tell me. There will be some filter bandwidth. Okay, you will get some filter bandwidth. Let's say it's a function of R1 and R2 both. Okay, I cannot solve this question for you, so that is why I cannot exactly say what is the filter bandwidth. You do it yourself. But let's say your filter bandwidth, um, let's say it's a function of let's say R1 and R2. It will be a function of R1 and R2, right? R1, R2 and C, isn't it?
Yes, sir.
Correct? So, but you know that none of these three you will get exactly what you wanted, right? You will have some variation around it. Hmm? So now if you have that, let's for time being say that the C is exactly what you wanted. So let's say C does not have any variation, but let's say R1 and R2 have variation. Now let's the company has said that the variation is of the tolerance is 10%, which means what? If you want to buy a product which is of 10 kilo ohms, you might get a product which is also of 9 kilo ohms, isn't it? The things
Yes, sir.
that you're actually buying might be of 9 kilo ohms or 11 kilo ohms. That's what. But but one thing that the company say guaranteeing is that these resistors, whatever their variation is, it's completely uncorrelated. Which means that let's say you buy one resistor here, R1, it has 10 kilo, it let's say is 11 kilo ohms. The other resistor that you buy after buying this one, you cannot guarantee what will be the, you cannot say anything about what will be the value of this. You cannot say anything about it. It's completely uncorrelated, independent. Got it? It can be 10.9, it can be 11.2, whatever. I mean 10.9 or let's say 9.9, anything. But you cannot say anything about it. Even after looking at this resistor R1, you cannot say anything about it, which means that the resistors are, the variation among them is uncorrelated. Got it?
Yes, sir.
Yes, and when you say but there is another kind of correlation, which is another kind of relationship, which is called correlated variation, which means that if you have okay, yeah, so let's say you buy one resistor here, okay, it was of 10 kilo ohm, let's say 10.1 kilo ohms, okay, and let's say there is another resistor. Now the information that I will give you is that these two resistors were prepared in exactly the same environment, nothing changed, no change at all. So can you tell me something? Let's say it is not 10.2, but let's say it is 10.9 kilo ohms. So can you tell me this resistor R2, when I will buy it, it will be greater than or less, it will be greater than or less than 10 kilo ohms? The information that I have given you is that these two resistors are prepared in exactly the same environment.
Greater than 10.
Exactly, right? It will be, I mean, this is something which is very logical, right? You will not be able to say what is the exact value of this resistor before testing it, but one thing that you can say with a lot of certainty will be what? That it will be greater than 10 kilo ohms, right? Because the R1 was greater than 10 kilo ohms, and these two are prepared in almost the same environment, in exactly the same environment, right? So this is called correlated variation. That this has a variation of, let's say, something. This resistor R1 has some variation, and based on that variation, R2 also is showing similar type of variation, something like that. You can say something. I mean, the meaning of correlation is that you can say something about R2 by looking at R1. That is what is meant by correlation. This is all statistical probability. If you have learnt probability, you must have heard correlation and all. Have you guys learnt ever about probability?
Sir,
Yes,
I
sir.
think at the end of the question, like they described the relation of correlation also, like how those two are related.
Okay, I have not seen. Yes, they have seen. That's what you have written here, right? If R and R2 have correlated tolerance of 10% around the values calculated in 1 and 2, determine the lowest possible DC gain in dB. Yeah, it is actually seen here, right? So hint, if R1 increases by X%, R2 also increases by X%. Right. So here they have actually exactly told what they mean by correlation. But in general, correlated tolerance doesn't mean this. Okay. In general, whatever is written here in hint, it is not true. It is this for this particular case. Okay. In general, correlated means by looking at one, you can say something about the other. That is correlation. Okay. So if
Yes.
so because of this hint, I think this question is straightforward. There is nothing to discuss here because it is very well very well understood here. You will be able to find the optimum value in this particular case. So try it out. If you're not, I will be able to. I'll talk about it in the next session. Okay. Anyway, so anything else? Because I do not have any problem to discuss today. It's just that there's nothing which can be made on that particular week lecture. Okay, so if there's nothing, I will maybe just let's end it today at this point only. We'll again come back, meet again next time. All right. The next week again the same time 6 to 8. Again on Mondays only. We'll meet again next week. All right.
So one
Yeah.
doubt, like
Yeah.
it is
Go.
regarding week 3. Can
Week
I
3.
ask
Yes.
it now?
Yeah. Yeah. Sure. Why not?
Yeah, so like see, we are doing analysis for ideal case, like there is no load at the output side. What is the analysis procedure, or what is the case if we have a load at the output? Suppose if we take the same negative feedback amplifier with
Uh-huh.
gains okay,
Mm-hmm.
and we keep some load at the output and the load is changing. So how will the analysis go? That's
Yeah. First of all, the thing is that that will come later. Okay. There will come a point when you will learn this. This will be a typical problem in this thing Miller compensated op amp. You will a two-stage op amp, you will learn about it. Okay, I think this comes in week 4 or week 5. You will learn about it there. But in this particular case, at least here I can clearly see that if you have an ideal op amp here, whatever you connect at the output doesn't matter, right?
yes.
Right. So let's take it. So another thing, even in the example that the instructor is talking about, he actually has put a buffer in between, right? There's a buffer in between between the output actual load where the load is connected and the negative feedback element, there is a buffer. If you go through the lecture, you will see
Yes,
there is a
yes.
buffer. Yeah, and that buffer design is not described right now. So for whatever, so at this point, just assume that the load is not making any problem, creating any problems. You will learn about it, the problems that are associated with the load when you have learnt about this two-stage op amp. Okay, there you will see it in great details.
Okay, got it. Yeah, thank you.
Yeah, welcome. Okay, so thank you guys. Thank you for joining. We'll meet again next time.
Thank
Thank
you.
you.
Thank you.